Good afternoon or good morning, gentlemen, whenever you are watching this. So this is a lecture of the first 2 days of lectures that we covered in our integrated science class. So my plan is I'm going to start trying to record these semi-regularly. So I'll do it after every lecture or in advance for you. But if you are not utilizing them, or people decide like, hey, I just don't really care about them anymore, I'm not going to record them because I'm not going to put in the effort for something that's not going to be used as an excellent skill or study set for you. So I need to see that you're participating in these in some way, even just emailing me further questions or redoing homework from the past. Excuse the bell. But ultimately, at the end of the day, I do need to see that you're participating through these. Otherwise, I'm not going to do it. I will be skipping over anything with the lab and any other pictures that we kind of discussed in class. I'll give you a brief discussion on them. However, I won't be focusing on them. This is primarily going to be notes. And as a reminder, all these notes are found on Canvas. So what is chemistry? Chemistry is experiments, whether that they are a failure or they learn something new and you discover something. It's about the atom. It's about what's on the molecular level for that in my subatomic particles. It's about my subatomic particles, so like neutrons, my shape of the atoms, and all things kind of funky, as well as explosions, which is crazy to think about. There's chemistry all around me. So in my cell phone, I can go and say, all of these elements that you see listed here are in your cell phone. Even if these are old, like a visual of a cell phone, you can still find these elements present in my microphone speaker, my display, my computer chip, and all of that, which is crazy to think about. Chemistry is around us way more than you realize, and that's why it's important you understand it. So we kind of talked about this in class, but I want to give you a reminder. There are 7 times 10 to the 27th atoms, which is crazy to think about, that we can say on average there are this many atoms present, when 200 years ago I didn't even know what an atom was. So it's just fun fact for you to really think about how present atoms are in your life. Now, I'm going to focus on the history of the atom. This is going to go by what feels very quick. However, please pause and rewind because there's a lot of information, yes. However, I do want you to understand what's going on. So we have 4 types of models. We do the marble model, we have the plum pudding model, but I don't like that name, so I equate it to a muffin, so call it the muffin model, but it's also known as the plum pudding model, the nuclear model, and then the planetary model. Dalton was the first one to discover the atom. We had Democritus, and he made a hypothesis about them. However, Dalton was actually able to study them and learn about them as a whole. And he came up with what we know as the marble model for an atom. And he discovered that atoms are indivisible. There's nothing smaller than an atom. They're made up of all things. So everything that we do is made of an atom. What I am, made up of an atom. My hair, atoms, which is crazy. They're also that atoms of one element are all similar and can combine with other elements to form compounds. So the oxygen, the air that I breathe, is one atom. It's all oxygen. And if I took hydrogen, so I had all my hydrogen atoms and I mixed them together, I'd get a compound because I'm combining my H's and my O's. He also discovered that atoms cannot be destroyed or created, which this is extremely important. I cannot go in a lab and create an atom. Those are things that just exist, and I cannot destroy an atom. So I talked a little bit about these images in class, so I'm not really going to focus on them too much. However, between the 2 models, I have one with a nucleus and one without. Thomson was our next guy, and he came up with our plum pudding model. So I like to equate it to a chocolate chip. He discovered about negatively charged subatomic particles, and those are our electrons. And he said, okay, we have a negative, meaning we have to have a positive. So his model, the idea is if I had a muffin or a chocolate chip cookie, the cookie or muffin part, that bread, is my positive, and my chocolate chips, my blueberries, whatever I add into it would be my electrons. So my electrons are just kind of stuck in there, and everything else is positive. And Thomson, his discovery was amazing because he found the electron using the cathode ray tube experiment, and he got a Nobel Prize for this discovery. So what he did is he put them in a ray tube, okay, a tube with a ray. And he had two deflecting plates. He had a negative plate on the top and a positive plate on the bottom. And when he showed, kind of made his ray shoot through it, he turned it on, he noticed, which was very interesting, that the ray was going towards my positive plate and away from the negative plate. Meaning I had to have something negative that was opposing my negative charge, but also attracted to my positive charge. And that's how we found it. He noticed that deflection, he made observations, and he was able to come to the conclusion that there was a negative subatomic particle, which he named the electron. So J.J. Thomson kept this for a while. However, he was not correct. So yes, we had a positive and now we had a negative compared to Dalton, where we didn't have any subatomic particles, but we're not quite there yet. And that's the important part about the history, is that we learn a lot more by experimenting and getting new instrumentation out. So the atom that we know today could drastically change in 100 years, which is crazy to think about. So Thomson came up with this model. A lot of people liked it. And it wasn't until Rutherford came along that we changed the model and we have our now nuclear model. Rutherford discovered there was a small, dense nucleus in the center of the atom, and that's where our positive charge was held. Our protons were located. He also said, well, if I have a positive charge in the middle, I have to have electrons on the outside. And those electrons were existing in what we call empty space. So the atom was empty space, where all the density of it was composed in the nucleus. Rutherford discovered this by doing a gold foil experiment. And essentially what he did is he set up the gold foil, he put up a fluorescent screen, and he started throwing a alpha particle source at it, like a little bit of a ray, and he noticed 99% of the time the ray was going through. But about 1% of the time it was deflecting. And the only way that we could have a deflection of source is if it was hitting off of something. So like my image on the right there. So those deflecting rays were primarily if it hit the nucleus. So that's why he was able to say and come to the conclusion, there's something positive in the center, and that's what's holding in my electrons, and that's what's deflecting my ray, that's where my density is at, and that everything else was empty space. And then I had this ed puzzle for you if you would like to do it. Those are some fun facts. Please pause this if you want to read it. Here's a little bit of a meta comment, but I really don't want to focus on these. I really want to focus on the content for you. So we have Rutherford's model, we have our nuclear model, but what are we still missing? So when I look between these two, I can see that I have a positive nucleus in the middle with electrons on the outside, whereas the other one I have neutrons, and I have protons, and I have electrons. Well, Chadwick came along and he discovered neutrons. That's what his important thing is. So he discovered neutrons exist in the nucleus and they were neutrally charged. So thank you, Chadwick, for that. However, his model was a little bit different. He didn't have the rings that our newest guy came out with. And that newest guy was Bohr. And Bohr has the planetary model. He discovered that electrons travel around the nucleus in specific paths that we call orbitals on separate energy levels. And he also said that the nucleus was composed of our protons and our neutrons, and it was in the center. So his model was similar to our solar system. We did the quiz. I'm going to go through that. So here's some basic anatomy now that we have what we call our Bohr model, and that's what we use to show atoms. It's a lot easier than going into our quantum model that we are currently studying. Like in science, we're not studying it, scientists are studying it. Let me scoot over here. So, cool. We have three subatomic particles. We have a proton, we have a neutron, and we have an electron. Protons have a positive 1 charge, they're our positive, and they have a mass unit of 1 AMU. AMU is the atomic mass unit, and it's just a mass unit we gave to protons and neutrons and electrons because they were so small and we're lazy and we don't want to type out 100 numbers to solve anything, so we just denote it with 1 AMU. And neutrons, they're in the nucleus, they have a charge of 0, and they are also with 1 AMU. It makes sense that they have 1 AMU because this is where our atomic mass is coming from, our protons and our neutrons. Electrons are in the cloud, they're outside of the nucleus, and these are denoted with a negative 1 charge, and they are equal to 1 divided by 1,840th of a proton. So essentially, we denote it with a 0 AMU, because we don't want to type that long answer, and the weight just is not significant enough to be counted in our mass. There we go. Proton and neutron equal. Electron and proton, I need 1,840 electrons to equal 1 proton. Elements are things that contain atoms with the same number of protons. So if I change my proton number, I change the element. So it's important to know the element on the periodic table with the atomic number, it cannot change. That proton number has to be the same so I can have oxygen. The atomic identity is our atomic number, and these are always our number of protons. So I already said this. If you change this, you change the element. Our atomic mass, is the number of protons plus the number of neutrons, and that's because electrons are too small, so we just focus on protons plus neutrons. When you look at your periodic table, the top number is your atomic number, and the bottom number is your atomic mass. And always round this to the nearest whole number. It's a lot easier. We don't want decimals. Now, this is something important. This is our chemical shorthand notation. So our shorthand chemical notation. The mass number is our red number, and it is a decimal because it's an average, but typically with our mass number, we round it to a whole number. And that is my number of protons plus my number of neutrons. My A on the bottom is my atomic number, and that's my proton number. The X is the chemical symbol for the element, and this can be found on the periodic table. It's between 1 and 2 letters. If I need to discover what the neutron number is, I would take the mass number minus the atomic number to equal my number of neutrons. Or if I'm given a number of neutrons and a number of protons, I can add them together to get my mass number. So we did an example in class. However, if I did the chemical shorthand for a carbon atom, I would look at my periodic table and see that the atomic mass is 12, 6 for my proton number, and C for my carbon. If I did a Bohr model, I would do 6 electrons on the outside, 6 in the middle for protons and neutrons. So I do 6 protons, 6 neutrons, 6 electrons. This is the candy atom model. And now we're moving on to ions and isotopes. Okay, so this video is posted in your notes. I would suggest going and watching it for your benefit. However, I'm not going to play it during this lecture because the audio gets really funky and the focus is our lecture. You did this activity for homework, and so I'm using it as a reference. However, we're going to start with isotopes. Isotopes are atoms of the same element with a different number of neutrons, meaning I will change my mass number in general when I do this based on if I have more or less neutrons, because I cannot change my proton number. So an example of this is that hydrogen normally only has 1 proton, but it can also have 1 proton and 1 neutron. If I were to look at hydrogen right now, the mass for hydrogen is 1, and the number for hydrogen is 1. So if it's just hydrogen from my periodic table, I wouldn't have a neutron, but if I added a neutron, the mass goes up to 2. So, yeah. What makes it remain hydrogen is that I never change my proton number. And I have 3 isotopes of hydrogen. So right there, I have 1 proton for protium. Deuterium is 1 proton, 1 neutron, and tritium is 1 proton with 2 neutrons. I have different isotopes of carbon. What's important to know about isotopes is that they can be stable or unstable, and you got a chance to really experience this in our Build of Atoms simulation. For carbon-12 and carbon-13 are considered stable, whereas carbon-14 is radioactive, which is crazy to think about, and we use that for what we call half-life calculations. So if I wanted to solve for the number of neutrons, I would have to look at the information in my shorthand. So yes, I have this, but in this case, this is my isotope. So typically I have about 95 for my mass for my molybdenum. However, in this case, I gave you a 97 mass with a 42 amounts of protons. So I want you to solve by taking 97 minus 42, and you should get 55 neutrons. Next, I'm moving on to ions. Ions are a charged atom. These are when an atom is neutral, like if I change the amount of electrons. So if the atom is neutral, the number of electrons should equal my number of protons. However, in an ion, I get a positive or negative charge due to the movement. So we have cations, which are electron loss, meaning it's more positive. So we use the little T in the middle as a plus sign to remember that it's positive. And an anion is when I gain electrons, meaning I have an overall negative charge. So for example, this is a neutral atom to an ion. If I start with a neutral calcium, I would have 20 protons and 20 electrons. But if I take away 2 electrons, I'm more positive. So I have 20 protons, 18 electrons, but a positive 2 charge denoted on that to show that change. So let's try a couple. Fluorine atom with 9 protons and 10 electrons. What's the charge? In this case, I have more electrons than protons. I have to have a negative charge overall. I have 1 more electron than proton, so I have a negative 1 charge. We just did this example, so a calcium atom with 20 protons and 18 electrons. I have more protons, meaning I have an overall more positive charge, and I have a positive 2 charge because I have a loss of 2 from 20 to 18. All right, that is all I have for you today. The rest of the stuff that we kind of covered was done in class up to here. So I hope that this helps you. If you have any questions, please email me. But other than that, at this point, if you're watching this on October 16th, this is your homework that is due on Monday and Tuesday for class. Have a wonderful day or weekend, and I hope you email me questions.